Somewhere 20,000 kilometers above your head, a satellite is talking to your phone.
How does it know exactly where you are? This is how GPS works.
Before GPS, finding your way meant looking up at the stars. Sailors used Polaris, the North Star, to figure out their latitude. A magnetic compass could point north, but it couldn't tell you how far you'd gone. Paper maps helped, but only if you already knew roughly where you were. Navigation errors of miles were common, and sometimes deadly. The GPS system starts with a constellation of satellites orbiting Earth. At least 24 satellites fly in 6 orbital planes, spread evenly around the globe. Each one circles the planet at about 20,200 kilometers altitude. They move at 14,000 kilometers per hour, completing 2 full orbits every day. This arrangement guarantees that at least 4 satellites are visible from anywhere on Earth.
That number, 4, turns out to be the magic number for GPS. More satellites mean better accuracy, and today there are over 30 in orbit.
GPS depends on one thing above all else: incredibly precise time. Each satellite carries 4 atomic clocks accurate to about 1 nanosecond. 1 nanosecond is 1 billionth of a second. In that tiny sliver of time, light travels only about 30 centimeters. A regular quartz clock drifts about 1 second per day. An atomic clock drifts 1 second in 100 million years.
That extreme precision is what makes GPS positioning possible.
Each satellite continuously broadcasts a radio signal toward Earth. That signal travels at the speed of light, about 300,000 kilometers per second. From 20,200 kilometers up, it takes roughly 67 milliseconds to reach your phone. The signal carries the satellite's ID, its exact position, and the precise time it was sent. It also includes health data, so your receiver knows which satellites to trust. GPS uses 2 main frequencies, L1 at 1575 MHz and L2 at 1227 MHz. Your phone's tiny antenna picks up these faint signals and starts doing math.
Here's the core idea. If you know how far you are from one satellite, you're somewhere on a sphere.
Add a second satellite, and those 2 spheres intersect in a circle. A third satellite narrows it down to just 2 points.
One of those points is usually out in space, so the answer is obvious. But GPS uses a 4th satellite to eliminate all ambiguity.
The 4th signal also corrects for timing errors in your phone's cheap clock. This process is called trilateration, not triangulation. With 4 satellites, your receiver solves for latitude, longitude, altitude, and time. 4 unknowns, 4 equations. That's why 4 satellites is the minimum.
The math is elegant. Distance equals speed times time.
The speed is the speed of light. The time is how long the signal took to arrive. Your receiver compares the send time stamped in the signal with its own receive time. Multiply that tiny time difference by the speed of light, and you get the distance. For example, a delay of 67 milliseconds means you're about 20,000 kilometers away. Do this for 4 satellites and solve the system of equations.
In theory, GPS should be perfect. In practice, several things introduce errors.
First, the atmosphere. The ionosphere and troposphere slow down and bend the signal. This makes the signal arrive slightly late, throwing off the distance calculation. Second, multipath reflection. Signals can bounce off buildings before reaching your phone. Your receiver sees the bounced signal as a longer path, adding meters of error. Third, clock drift. Your phone's clock isn't nearly as precise as an atomic clock. Even a tiny mismatch in timing translates to significant position error. Engineers have built clever systems to correct these errors. WAAS uses ground stations to measure atmospheric delays and broadcast corrections. Differential GPS compares readings at a known location to calculate the local error.
Nearby receivers can then subtract that error from their own readings. And here's a wild one. Einstein's relativity affects GPS.
Satellite clocks tick faster due to weaker gravity, gaining 38 microseconds per day. Without correcting for relativity, GPS would drift 10 kilometers per day.
GPS isn't just for finding your way. Its precision timing runs the modern world.
Banks use GPS time to stamp financial transactions down to the microsecond. Cell towers and power grids synchronize using GPS clocks. Farmers use centimeter-level GPS to guide tractors across fields automatically. Search and rescue teams locate emergency beacons using GPS coordinates. Scientists track tectonic plate movement, just millimeters per year, with GPS. GPS was built by the United States starting in 1978. But it's not the only system. Russia operates GLONASS with 24 satellites. The European Union built Galileo, 30 satellites with centimeter-level accuracy. China's Beidou system has 35 satellites, the largest constellation of all.
Your phone actually uses all 4 systems at once, over 100 satellites combined. So here's the whole picture.
Satellites with atomic clocks broadcast signals at the speed of light. Your phone measures the travel time and calculates the distance to each satellite. 4 satellites give you latitude, longitude, altitude, and precise time. Correction systems fix errors from the atmosphere, reflections, and relativity.
All of this happens in milliseconds, billions of times a day, all around the world.